This is a quick review for the math physics test for Georgia Virtual School Physics A/B, or it would work for Physics A as well. You need to know the 7 base SI units, and these are not meter, liter, gram. They're not the units without prefixes. They are the 7 units that scientists have agreed world over to use in their calculations and communication. So we're not talking about ones without prefixes. We're talking about candela for light intensity, ampere for electric current, meter for length, kilogram for mass, mole for quantity, Kelvin for temperature, and second for time. If you're given a quantity and it's not one of these units, you need to convert it to one of these units before using it in a calculation. So if you're given grams or centimeters, you need to convert those to kilograms or meters prior to using them in a calculation. You need to know these metric prefixes, their symbols, and the power of 10 that they represent. Micro is 10 to the minus 6. The symbol is the Greek letter mu. So that symbol means micro. And 10 to the minus 6, that's 1/1,000,000th. So it takes 1,000,000 micrograms to equal 1 gram. Milli means 10 to the minus 3rd, or 1 over 1,000. So a milligram is 1/1000th of a gram. The symbol is the lowercase m. Centi is 1/100th, 10 to the minus 2nd power. A centimeter is 100th of a meter. These are our 3 big prefixes. Giga, the prefix is capital 10, and it's 1 times 10 to the minus 9th. So 1 with 9 zeros. So there are a billion gigameters there are a billion meters in a gigameter. Mega is million, 10 to the 6th. So there are 1,000,000 meters in a megameter. A gigabyte is a billion bytes. And kilo is times 10 to the 3rd. So a kilometer is 1,000 meters, and the prefix is lowercase k. Notice milli is lowercase m, mega is uppercase m. Derived units are combinations of the base units. So like meter per second is a derived unit. A newton is actually a kilogram, meter per second squared. They are base units that are multiplied or divided to get more complicated units, and these are derived units. Converting within the metric system, you set up your T-chart. Sorry, I'm a little crooked here. So if I want to take 125 milliliters and convert it to liters, I need milliliters in the bottom so that they'll cancel nicely. And there are 1,000 milliliters in 1 liter. And so I divide 125 by 1,000 and get 0.125 liters. If I want to convert 12 liters to microliters, then I put my given here, 12 liters, and I want my liters to cancel, and I want microliters to be my unit. There are 1,000,000 microliters in 1 liter, and so there are 12 million. 12 million microliters in 12 liters. Notice the liters cancel, leaving microliters as my answer. Up here, the milliliters canceled, leaving liters as my unit. And convert 0.25 megagrams to grams, 0.25 megagrams. I need megagrams down here to cancel. Grams are the units that I want. And there are 1,000,000 grams in 1 megagram. And so if I move my decimal 6 places to the right, that's 2 places, 1, 2, 3, 4 places more, 1, 2, 3, 4, 5, that's right. 250,000 grams in 0.25 megagrams. Counting significant figures. You know that the only thing that you have to worry about is the zeros, because if it's not 0, it's significant. Zeros, the only time zeros are significant is if they are in between. So if I had 1,012, that 0 is significant because it's between 2 significant figures, or if they're on the right-hand end behind the decimal. So 1.021350. This 0 is significant because it's on the right-hand end behind the decimal. And this 0 is significant because it's in between 2 non-zero digits or 2 significant digits. And so this whole number would have 1, 2, 3, 4, 5, 6, 7 significant figures. So let's count these real quick. This has 2. These zeros are not significant. This has 3. This 0 is significant because it's between 2 significant figures. This has 1. None of these, you start at the left-hand side and go until you get to your first non-zero, and that's where your significant digit starts. That 2 is the only significant digit. I'll do the same thing here, and that 2 is significant, but that 0 is as well because it's on the right-hand end behind the decimal. There are 2 significant figures. And 0.2 is only 1, again, because this 0 is not significant. When we do math with significant figures, there are 2 rules, one applying to multiplication and division and one applying to addition and subtraction. Multiplication and division, your answer can't have more significant figures than the least in one of the numbers you're multiplying together. 2.5 has 2 significant digits, 42.93 has 4. When we do this on our calculator, we get 107.325, but we have to round it to 2 significant figures. That 1 is significant, I need a significant figure there, and so I'm going to round that to 110. It's 2 significant figures. The addition-subtraction rule is a little bit different. It is that your answer cannot be more precise or go out to a smaller place value than the least precise in the numbers you're adding or subtracting. This 2.5 is precise to the 10th place, 42.93 is precise to the 100th place, so our answer can only be precise to the 10th place. So 45.4 would be the rounded correct answer for that one. Scientific notation, hopefully you know how to do this already. You have to write it in standard scientific notation, which is 1 digit, a decimal, and then all of the other digits. And so this would be 2.48537 times 10 to the, well, let's see how many places we moved our decimal. We moved our decimal 1, 2, 3, 4, 5 places to the left, so times 10 to the 5th. Taking this number and writing it in standard scientific notation, it's going to be 2.34 times 10 to the something. How many places we move our decimal? 1, 2, 3, 4 to the right, so that's going to be a -4. When you multiply, just use your calculator and then round off to have the right number of significant digits. So when I do 7.8 times 10 to the -3, and I multiply that by 5.2 times 10 to the second, I get 4.056. But I need 2 things. I need it to be in standard scientific notation, which would be 4.056 times 10 to the 0th power, since I don't really need to move that decimal at all, and 10 to the 0th is 1. But this has too many significant digits. This had 2, this had 2, so this is going to round to 4.1 times 10 to the 0th power. In the next one, I got 1.8 times 10 to the 2nd power times 6.5 times 10 to the -1st, and I get 117. To write it in standard scientific notation, it'd be 1.17 times 10 to the 2nd power. And to round it to have the correct number of significant figures, I need 2. So that's going to be 1.2 times 10 to the 2nd power. When you graph, in physics, we use line graphs almost exclusively. We don't use bar graphs or pie graphs or scatter charts. We use line graphs. Every graph must have a title, labels on both axes, plotted points, and a trend line. So you'll have a graph, it'll have a label, and a title. It'll have plotted points, and it will have a trend line. You'll have questions on the test that ask what's missing, and so a graph will look like this, but it won't have a title, so the title's missing. Or maybe it has the trend line, but it doesn't have dots, then the plotted points are missing. Or it has dots and it doesn't have a trend line, then the trend line's missing. There are 4 things that it has to have, and you need to be able to identify the missing thing. When you graph, you plot the independent variable or the manipulated variable on the x-axis and the dependent or the responding variable on the y-axis. But if you are told to graph A versus B, then A has to go on the vertical or y-axis, and B has to go on the horizontal or x-axis. If you have a point that's an outlier, plot it. Like if I were plotting this data and there was a point way down here that didn't match the other at all, I would ignore it when I draw my trend line. You plot it, but then you ignore it when you analyze your data. This is a good example of a lot of things about a graph. I put it up there so that we could practice reading graphs. Where is the object at 1.5 seconds? This is a distance versus time graph at 1.5 seconds. That's right here. We go up. I would use a ruler. And so we hit right there at 1.5 seconds. And so it must be at 8 meters at 1.5 seconds. The other thing you can read is when is the object at 6 meters. So we start at 6 meters here and go out until we intersect our trend line, not our data. And then we go down, and that says that at about 3 seconds, it was at 6 meters. Remember the 4 things. It has a title, it has a label on the y-axis, it has a label on the x-axis, it has these nice little plotted points, and it has a trend line. And it has an outlier. Do you see how it has an outlier over here, but that doesn't affect the trend line? And again, I've already said this, you'll be asked to determine which of the 4 things is missing, so make sure you know what 4 things are required so you'll be able to answer that question. Types of trend lines. There really are only 2, rule or straight, perfectly straight lines, or curves. So if you're given more options than that, when you're asked what type of trend line would be appropriate, ignore the other 2, and these are your only 2 appropriate answers. So if I have a graph, and the data looks like this, then that is obviously, I think, a smooth curve. That's not a great trend line for that data, but this data indicates an increasing slope. So it would use a curve. Another case that might use a curve is if I have data that looks like that, then you had a graph on your Penny's lab that looked like this. That would be a smooth curve. If it's going to be a ruler straight line, those points need to be in a line with maybe 1 or 2 exceptions. So on the test, you'll see points that look like this, maybe one jotted up a little bit, maybe one a little bit low. But you'll look and see that most of the dots could be joined with a perfectly straight line. And so the answers for these, this one, the appropriate line would be a curve, trend line. This one, the appropriate trend line would also be a curve. In this case, it would be a straight line, and you can tell because those points really do, with the exception of 1 or 2, but not the majority. You see here, the majority are off of that straight line. So here, the majority are on that straight line, and that's what you're looking for. I believe that is the last slide. I hope you found this review helpful.